Hello everyone, welcome to Arden Labs Rust Safe at Any Speed webinar. We're going to be talking about how Rust adds safety at every layer of your stack, how you can use it to protect yourself, protect your program, stop too many people from breaking in and running all sorts of software that you probably don't want them running on your computer. It's going to be a fast ride because we've got a lot of content to go over in 1 hour, so buckle up and let's see about getting Rust safe at any speed. All right, first of all, who am I? I'm Herbert Wolverson. I'm the Rust trainer and consultant at Arden Labs. I'm responsible for the Ultimate Rust Foundations classes, all of the content in the Rust bundle. If you want, I will fly out and train you in person, or I'll train you over Zoom. I love training. I'm also the author of Hands-on Rust and Rust Brain Teasers with the Pragmatic Publishers. There's another book coming out very soon. I just found out the title will be Advanced Hands-on Rust. I unfortunately can't give you a release date yet, but it's coming imminently. I'm also the author of the Rust Roguelike Tutorial, lead developer of the open source project LibreQOS and BracketLib, and I contribute to open source projects all over the place. Really anything that takes my interest, looks like it could use some help. I love helping. Drop me a line if you have something you want me to help with. All right, what are we going to cover today? We're going to start with Rust's strongest point, memory safety. In particular, I went over and looked at some of the top CVEs, vulnerabilities, for what has been knocking services off the internet, or worse, taking them over and doing terrible things over the years. And the number one, of course, always used to be bounds checking and buffer overruns. That's pretty well handled by a lot of languages, but we're going to look at it. We're going to look at use after free and what that means, what it can let you do. We're going to look at use after move, which is more of a problem in some of the newer languages and newer versions of C++. We're going to look at type coercion and how it can result in your having data that you don't expect to be the data that you currently have, and that ties into overflows. And while that's not a vulnerability in itself, it quite frequently develops to be a vulnerability at the next step, because you can trick the system into having some data that isn't what you expect it to be. That gets passed on to the next stage. Things you don't expect to happen start to happen. We're going to talk a little bit about how Rust's pedantry really translates to clear intent, clearly stating what you want to do, making it obvious at both the caller and the callee, overriding, removing the risk of somebody further upstream changing the function signature, accidentally blowing away your memory, accidentally changing what's happening, possibly even violating some type safety, causing data loss, causing problems. Then we're going to dive into data races and what fearless concurrency does, and how Rust protects you from that, and how that allows you to write high-performance concurrent code and still feel safe, sleep at night, knowing that Rust is probably not, in fact, corrupting all your data, crashing the system, and causing all kinds of headaches. I will, of course, try and end with some general advice, and there'll be a QA at the end and a raffle to give away access to the Ultimate Bundle. Okay, memory safety. So what does memory safety really mean? Memory safety, at some level, affects every single programming language, even the safe ones, like Go, Java, C#, because at some point, somewhere, something has to allocate memory in your computer. Buffers are sized. Writing beyond the end of a buffer, well, that can be bad because you might be corrupting your existing program. Reading beyond the end of a buffer, that can be bad because you might be leaking whatever data is adjacent to it in your computer's memory. At best, you'll get a crash. At worst, terrible things happen, and you find out that your beautiful server is now serving out viruses from Turkey. That happened to me back in the 2000s. Let's try not to have it happen to you. You don't, and so memory safety issues in C and C++ were very much the driving force behind the creation of Java, then the .NET family, Go, and Rust. Rust itself is very much a response from Mozilla to how well C++ was working out for them. I just saw the question, if it compiles, it works. Is that true? That is a beautiful tie-in to our next set of slides, where you'll see why that can be a problem with some languages. All right, let's have a look at some C. Got a nice simple C program here. set up a function called main, make an array of 5 numbers, loop from 0 to 10, print out each of the array items. Now the good news in answer to Angel's question, if it compiles it works, is this compiles perfectly. I even compiled it with -w all to show every warning that GCC would possibly want to spam with me. It informed me that this program is perfectly fine. I have nothing to worry about whatsoever. So here's the downside. It shows through 0 to 4, it shows 1, 2, 3, 4, 5. That's what's in my array. And location 5, 0. Location 6, huge number, 1795, and so on. Location 7, 105. So the problem here is we have got our array sitting on the stack. C has happily let us read to that, and then read into the next memory location, keep going. We're actually reading other parts of the program. We're reading some data that really shouldn't be in that array at all. Problem here is that C treats arrays as being a pointer. It doesn't even store the end. There's no bounds checking. If you forgot to do the bounds checking, your program is dangerous. You can potentially leak some information. If we were writing to the array, it'll happily let us write past the end of that array. Best case, it crashes. Worst case, we just corrupted our program. That's how a lot of buffer overrun exploits work. So how about C++? C++ is gradually adding a fair amount of safety on top of C. Biggest issue with C++ is that it's a beautiful language, but it's a beautiful 5 languages over the years, because we've got C++, C++ 2011, 2013, 2017, 2020, 2023 is coming on. But they never really remove anything, so over the years we've got more and more options coming in, and all of them do provide some safety, some of them don't. So let's go ahead and use a vector of integers. A vector is like an array, but it stores it on the heap. It does store the size, capacity, it's dynamic, you can grow it, you can shrink it back down, and we'll just go through 0 to 10, reading the memory. And oh dear, we have exactly the same problem. We list the first 5 numbers, then suddenly we see a 1041 and a couple of other big numbers. So now we're reading into the heap outside of what we think this vector should be accessing. And that's not good either. And once again, when I compiled this, I didn't get any compiler warnings. So C and C++ clearly have some issues here. Now there is some good news. C++ has a lot of safety options. You can use them. The problem is they're all opt-in. Bjorn Strassrup was talking about this. C++ has most of the safety options that you can find in other languages. On Rust, you have to opt out of them explicitly, mark them as unsafe. On C++, you have to remember to use them and opt in. So if you use the @index instead of just index, so in the code here you've got std vector, and instead of referring to numbers with the square bracket, we're using the function. It actually throws an exception when it reaches the end of the loop. So the program crashes with the error message std out of range. You could be catching that exception, you could be choosing not to crash. The great news is it will not be handing out information that it shouldn't be handing out because it has done a range check. It's good to go. It's safe. So you can opt into safety. The question then becomes, should you have to? So we have a look at Go. Great news is that the Go compiler is smart enough to absolutely not even compile when I try and read outside of the array directly. So you can trick it by using a loop. The loop prints 0, 1, 2, 3, 4, panics with index out of range, which is perfect. It's exactly what you want. Go won't be leaking your company secrets. This way, it's always better to panic and to crash and optionally catch the error than it is to inadvertently hand parts of your computer's memory out to the internet to do whatever they want with. Okay, so looking at Rust, it's kind of similar to Go. You let array equals 0, 1, 2, 3, 4. Try and print the 5th element that doesn't exist. Will not compile. The compiler is smart. It does a little bit of static analysis and realizes that index can't be right. The compiler is not that smart, though, that if you build a loop, it doesn't realize that that's going to panic. We'll still let you print. But then it panics with an index out of bounds instead of exposing your data. So perfect. Rust has passed the lowest bar of memory safety. It's not going to be letting you read outside of the outside of your variables. You're not going to be, and this protects you from an awful lot of vulnerabilities that have happened over the years, thousands and thousands of them. If you search for buffer overrun, out of bounds error, and similar on CVE databases, you will see that over the years, these have been responsible for absolutely ridiculous numbers of exploits, vulnerabilities, crashes, and problems over the years. So, a question I get quite asked quite often is, I'm using Rust because I want performance. But how do you have performance if every single time I access an array, I'm looking for index is inside array.length, I'm adding a runtime check to every single time I access that array, it slows my code down. So first of all, if somebody's telling you that, tell them absolutely that they need to get out a profiler and measure with and without bounds checking. Because modern compilers are really, really smart. They do a wonderful job of realizing, hey, that's a bounds check, figuring out what the upper bound of your loop is, and alighting it to only do the bounds check a couple of times, once, if necessary. But that's not always true. So if your profiler tells you that yes, because I am iterating through a million array items, I'm accessing them by index each time, doing something with them, that's a million bounds checks, and this is something critical, needs to be super fast, you absolutely can opt out of safety in Rust. But to do so requires that you put the unsafe tag, because now you're opting out of the safety features. And then for your array, you can call getUnchecked, hand it the index. And the bad news is, because this is invalid, it prints 0. So we've opted out, and we've chosen to have the same level of issues as C and C++. And that's a good thing and a bad thing. It's a bad thing in the sense that obviously you don't want to do this. It's a good thing because Rust is a real systems language, and sometimes you actually need to be able to drop down, do some really scary stuff because you're interacting with some bizarre hardware. Maybe you're writing kernel modules for some brand new piece of kit that's coming out. And sometimes hardware doesn't always obey the rules that you expect, and you really do need to be able to write arbitrarily to some piece of memory to do something. Or if you can be absolutely 100% sure that you are not going to violate the precondition, opting out of checking that precondition might get you a small performance boost. Most of the time you don't need it. Profile, if you can convince everyone that you really do need it, you've got that escape hatch to turn the safety off. And please, please, please write and put the unsafe block in, and also write your safety comment saying why you did it, why you opted out, and why you're convinced it's safe, so the next person who comes along and looks at your code says, oh, that's unsafe, and deletes it, understands why you did it, and hopefully the performance benefit was real. You can put it back. Okay, use after free and use after move. So what is this? When you're allocating and deallocating memory on a systems level, you're typically calling down at some point to the operating system memory allocator, which you're saying, give me a block of memory. At some point in the future, when you're done with that block of memory, you say, okay, I'm done with it. Delete that block of memory. Now, Rust and C++ have largely solved the memory leak issue with RAII, resource acquisition resource acquisition is initialization, and or reference counting. Garbage collected languages skip the whole problem by handling the deletion with mark and sweep and similar algorithms where they look to see what's in use, get rid of it. But if you're writing a low-level systems code and you need to allocate some memory and you deallocate it, a surprising problem is you deallocate something and then you try and use it anyway. And this happens all the time in particularly C and C++, but it can happen in other languages too. If you're allocating something to the heap and you have basically a pointer, that pointer might have become null, in which case you get a dereferencing null issue, usually a crash. Or it might be a pointer to some arbitrary piece of memory that is no longer what you thought it was. At that point, it's anybody's guess what's going to happen, and that's not going to lead to a good day. On a bad day, You might find yourself on the CVE database, and that's generally where you don't want to be, the common vulnerability list. So here's a very simple example in some C++. Made a structure. My class is new, my class. We've put it up on the heap. And yes, I know all about unique pointer, but we'll talk about that in a moment. We set data inside our class to be 5. We delete A, and then we print data. All good. Compiles with no warnings. So yep, if it compiles, ship it, right? Well, here's the thing. This doesn't crash on my Linux machine that I wrote this on. It prints out a big number starting with 161033. I have no idea what that was. I didn't go digging with the memory allocator to find out what. In the online C playground, it segfaulted and died. So you've created an object, you've deleted it, and then you've tried to use it. Believe it or not, this is a very common problem. If you go through the bug list history for Mozilla, you can see why it inspired some of them to come up with Rust. Modern C++ elides the problem. You can use unique pointer to guarantee that RAII won't let you forget to delete. That's awesome. You set data to 5. Now, most of the time you will never call the release function, but you can. Release specifically tells the C++ system, I'm done with this pointer, delete it. Still compiles with no warnings. It still gives a segmentation fault and crashes when I run it. And like I said, we're not going to talk about Go because Go is not going to let you allocate something, delete it, and access it because Go is managing your memory for you. And a lot of the purpose of Go was to make sure that this sort of problem stops plaguing the internet. So Rust makes this a little more complicated. Rust has RAII, the C++ unique pointer system that you allocate something, it's attached to a smart pointer. As soon as that smart pointer goes out of scope, the memory gets deleted. Memory leaks are really hard to achieve unless you use std memory forget or the beautifully named command leak, which is built into the smart pointer type box for those odd occasions that you actually want to leak some memory, which does happen on very low-level code, but in my opinion really should be marked as unsafe. So let's have a look at this first program. We make a class, we set some data. It's just like the C++ program. We allocate ourselves a class, we drop it, it's on the stack, not the heap. We try and print the data. Good news, this will not compile because Rust is actually tracking that we've created the object. Rust is tracking that now the object no longer exists. And one of the reasons the Rust compiler takes a little longer than some other compilers is that for everything you create, it actually tracks the lifetime of how long that object sticks around and can it be accessed safely, which we'll talk about in a little bit. Just in case you thought that I was cheating by using the stack, the second one here is the same thing, but I use a box, I put it up on the heap, drop it, still won't compile because Rust has kept track of the ownership and existence of this all the way through. It simply will not compile. There's no garbage collection, deletion remains deterministic. I saw Bill just said if you can pay for GC, you should consider Go. I agree. And Rust is great when you need to worry about deterministic latencies, really need to get down to what I think of as systems level, interacting with the kernel, interacting with devices, pushing for high performance. The two can live together hand in hand, go really well together. So use after move doesn't exist in C because C doesn't have a move construct. C++ introduced it and caused a huge amount of confusion. This is the point where I'm in a hall and I ask all the C++ programmers to put their hand up if they really know what std move does. And the sad thing is, this is where I stand there and there's usually silence or one or two people sheepishly putting up a hand. It's not always great. Because moving doesn't necessarily do what you expect. Moving may copy the data, it may not. All std move in C++ does is it marks a variable as now being what's called an X value, meaning it has been moved from. It might still be intact, it might not. The only guarantee you have is that it still exists in sufficient state to delete. So, it may have been plundered, it may not, you don't know. C++ has introduced this, and because of the way unique pointer works, if you want to be moving your data around, you have to move the ownership of unique pointer, because unique pointer, like Rust, has the concept that I own this variable, it's mine. When I either move it to someone else, it becomes their problem, or I drop it, I stop using it, it goes out of scope, it will be deleted. So here's a piece of C++ that I don't recommend you write. We've got a function, do something, accepts a unique pointer to a class. We make a unique pointer, we set it, we move the instance of my class into do something. Do something now owns that. So what happens when we do a print and print that data? Now the answer is undefined behavior. We honestly don't know what it's going to do. When I ran this on my computer, it gave me a segfault. When I ran this on a different computer belonging to my wife, it printed 5. It's not defined, you don't know, you can't rely on it, it's kind of dangerous. So in Rust, what happens when you do this? It won't compile, because Rust tracks the ownership and the lifetime again. It's what the borrow checker is doing, why the borrow checker annoys you when you first start, because it is quite pedantic and will not let you do a lot of dangerous things. But Rust tracks this in great detail all the way through your whole program. So you cannot make a use after move bug in Rust or in safe Rust in any way that will compile without the compiler simply refusing to make the binary at all. You can't run. Again, search through a CVE database. You'll see that use after move has caused all manner of problems, to the point that sometimes you'll find C++ forums debating whether or not move was a bad idea to begin with. All right, overflow and underflow. For those of you who don't know what this is, let's do a quick rundown. Numbers inside your computer are stored in binary with a number of bits. So if you have 8 bits, that allows you to have 0 to 255 if you're doing unsigned. If you're doing signed, then one of the bits will represent whether or not the number is negative. And you can get slightly surprising results if you just do binary arithmetic and ignore the issue of overflow or underflow. So 255 plus 1 frequently evaluates to 0. 0 minus 1 frequently evaluates to 255. If you're calculating numbers that are used to index a buffer, this is a perfect way to then trigger the issues we just talked about before. And just in case you wondered how bad this issue could be, between 1985 and 1987, an arithmetic overflow bug in the Therac 25 radiation therapy machines caused the death of at least 6 people from radiation overdoses. In August 2016, a casino machine at Resorts World printed out a prize ticket of $42,949,000 on a machine with a maximum limit of 10,000 payout. Fortunately for them, turns out software bugs win in court, and they just win in court, and if you've posted your maximum, you just owe the maximum. But it's not all bad. On Lamborghini American Challenge on the Super Nintendo, you could underflow your cash by spending too much money too quickly, and wind up with $65,535 in your account because you spent too much. I wish the real world worked like that. So in C, C++, and Go, by default, if you take an 8-bit number, I've used the standard C int just to make it a little more obvious in the C code that I'm using an unsigned 8-bit number. I add 1 to it. I get 255. 0 minus 1 gives me 255. Same with Go. Now, if you're an experienced programmer, you're used to how this works, no big deal, and you can write some code to catch that if it's important. Not a problem, right? And generally speaking, if you've been programming for a while, you know to do that. That's great. You can build your own seatbelts. Well, I personally like my seatbelts to come in pre-installed. So let's give that a go in Rust. Rust gets halfway here. So let n u8, so a uint 8, just like the others, 255, print n plus 1. Well, this doesn't compile at all because the static analyzer has figured out that n plus 1 is going to be an invalid number, and so the compiler will actually refuse to compile it altogether. So we got a little tricky, throw in a loop. Now the static analyzer is not analyzing in enough detail because we want to compile today, not next week. And unfortunately, following every possible code flow would be a case of cargo build and go on vacation. So we let mutable n equal 0, and we add 1 to it 257 times. And what happens? Well, the answer is, if you're in debug mode, the default, so you've typed cargo run, you get 0 to 255, and then the program panics with the message attempt to add with overflow. So it's tracking the bit that gets set when you overflow in your CPU, checking it, printing it out. Now this is a slightly slower operation. So in release mode, the compiler optimizes that away. And in release mode, when you do cargo run ---- release, print 0 to 255, and then 0 again. So the wrapping happened. So, I always tell students that when you're in Rust and you're doing arithmetic that might wrap, always run your code at least once in debug mode. I have had production systems surprise me by crashing and showing me that some code that I thought had been working for months did in fact have this problem. It's better to find it, solve it, and not have the problem. So, you're a Rust user, but what if you want to overflow? Well, the assumption is that for newer programmers in particular, overflowing might be surprising behavior. And one of the core concepts of Rust is, I don't want to surprise you. Your Rust will try not to do surprising behavior when possible, if you ignore the syntax, which to many people is pretty surprising. So, what you could do is write the code we have there on the left. Result equals a plus b. If a is greater than 0 and b is greater than 0 and result is less than 0, then we know that it didn't wrap. That works in most languages. That's pretty much in line with what happens when you use one of the libraries that adds wrapping support or overflow checks for you. Rust decided that we were all sick of typing those, and in the standard library added some checked and saturating arithmetic. So we have this little example here. Set n a U8, you unsigned 8-bit integer to 255. We call checked add. And checked add returns an option. It'll return sum and the result if the result is valid, and return none if it would have resulted in an overflow. This gives you a way to not panic at runtime, check to see if it happened. But what if I want to wrap, want to overflow? That's quite common in some algorithms. Some algorithms are built on the assumption that your computer will behave that way, whether it's defined behavior or not. If you ever want to poke at some C++ people, talk about whether or not unsigned integer wrapping is in fact undefined behavior. Wrapping, n.wrapping add 1. You're telling the compiler explicitly, I want wrapping behavior. Wrapping is not an error. And to me, that's great because you are signaling your intent, not just to you, not just to the compiler, but to the guy who comes along a few months later, reads your code, is trying to figure out what's going on. He can clearly see that this is what I intended to happen. Likewise, they added saturating add. It's also not an uncommon pattern to say that I can accept up to 255 in this field. If the result would be 280, I still want to keep 255 because I just want to represent that I've hit the maximum value for this type. And that's what saturating add does. So running this little program, first one tells you adding would have resulted in an overflow. You've caught the problem. Using wrapping, you've declared that what you want to happen. Awesome, it wraps. Using saturating, awesome, it saturates up to the maximum. There are additional checked division allows you to perform a division and have to check at runtime for this isn't going to work because dividing by 0 is not a good plan. You can saturating subtract, wrapping subtract, multiply. They're all covered. They're all there, right there in the standard library. There's also an additional type that you can write the long-winded wrapping and then the angle brackets to indicate a specialization and a type inside. I personally don't use that because I find the function named system a little easier to use. If you prefer the other, it's right there. All right, let's talk a little bit about type coercion. So converting between types is more tricky than you might think. We talked about how adding 1 to 255, getting you 0, is surprising if you're not a programmer. Well, this one surprises a lot of people who find themselves just getting into the C world. So we make a 16-bit integer, we allocate it, we assign it to be 260. And then later on, usually there's a few hundred lines of code in there just to confuse you. You usually don't line it up to be quite as obvious as this example. You have made a smaller integer, and you assign it to be the value of the other one. And so this program will confidently compile with no errors or warnings, and confidently tell you that 260 is equal to 4. That may not be the behavior you're expecting. The good news is that in this simple form, you can get GCC to give you a warning if you enable all warnings. Go and Rust protect against this by making it a little harder to inadvertently assign from one type to another. In C, it's called type coercion because you are literally coercing one type to fit into another and just dropping any additional data that's in the way that won't fit. You didn't need it anyway, right? So in Go, 16-bit number 260, 8-bit number O, print the 2 out. It's disallowed, won't compile, you get an error message. Rust does the same thing. Both tell you that you have a type problem. The Rust message is a whole lot more long-winded, but they both boil down to the same thing. Now the downside of this is when you want to transform from a smaller type to a bigger type. This is actually always a safe operation, because if you're going from an 8-bit number, the entire range can always be an unsigned 8-bit number. The entire range can always be expressed by an unsigned 16-bit number. But both Go and Rust, because of that protection, will actually complain and tell you that going from one type to the other can't be done without a cast. You probably don't want to do it. The Rust message does at least give you a clue as to what command you should use to do this. So the most easy way to do this is to force the issue. We're going to declare, so here in Go we just say uint8 n, force it in there. In Rust we'll say as u8. And at this point, there's been a huge debate in the Rust community as to whether as should actually be unsafe. It's currently not, because that would litter an awful lot of existing code with unsafe. But it can lead to data loss, because by typing that as, or in Go, by typing the uint8, you're telling it, I understand what's going on, hold my beer, do the conversion. And so now 260 in both languages does equal 4 as well. That's great, you can join the C Club. If that wasn't what you intended, then let's hope that you remember to write some extra checks before you force the code, before you force the number, and that you understand your program well enough to know that you're not going to have that problem and what to do if you do. So Rust tried to make this a little easier by having a trait called into. Now into allows you to say variable name dot into, and the compiler will try and figure out what it's being converted into. And if there is a implementation of that trait to go from one type to another, it will automatically work. So in this tiny example, small u8 255, big u16 small dot into will work, because going from a u8 to a u16 is safe. And Rust has carefully and painstakingly added in entries for all of the safe conversions that will not fail, and it hasn't entered in conversions for all of the ones that are unsafe. So if you try and do big u16 into a u8 with into, will not compile because that's not implemented. And so Rust introduced a second one. I know Rust complexity can be a little overwhelming sometimes, but it's often because of cases like this where into only provides the safe ones, but sometimes it's safe, sometimes it's not. So you have a 16-bit number that is 250. It can be converted into a U8. You have a 16-bit number that's 260. Well, it's not going to fit into a U8. So maybe when you're converting your numbers, you want a way to know, will it fit, or am I going to have an issue? Am I going to potentially lose some of my data, or worse, mess up the what system I'm using for indexing into an array and cause all the problems that we had before? So try into came along. Try into is the same as into, with the exception that it returns a result, and the result will be OK and the valid number, or it will be an error telling you that you can't convert the number. And so you can come up with something like this, where I create a set of numbers from 250 to 260 in a U16, convert that into an iterator flat map. And what flat map does is it says just keep the good ones, throw away the errors, and collect it, print it out. It just shows you 250 through 255, the valid conversions. It successfully detected that the other ones weren't going to work. A lot of the time, you'd actually want to check the errors and maybe do something with them. For the sake of example, though, what we're showing here is that Rust gives you the way to track the problem, keep a hold of it, and do the right thing. And what the right thing is, of course, depends on your program. All right, we talked a little bit about this, clearly indicating intent. And I've captioned this, oops, that function changed my variables. Sometimes being pedantic is good because you're clearly indicating what you expect to happen. You're not indicating what you hope will happen. And you're not indicating what you expect to happen based on the code last time you looked at the function signature of the other guy who wrote the library you're using. A surprising number of bugs are found at the boundaries between between functions and libraries, particularly if either somebody else wrote the other function, very common in a company, or if you're making use of other libraries, or you wrote it several months ago, you don't quite remember because it's been a while, you've done a ton of stuff in between. Sometimes you can be your own worst enemy. You may have written some good documentation. Hopefully that helped, because hopefully you remembered to read it. Sometimes, though, it's surprising. So you can always help with this by using some comments, but there's no promise that anyone will read them. By clearly flagging, wrapping, saturating, and checked arithmetic, you make it obvious to the next person to use your code what you expect. By clearly flagging conversions with into or try into and not using as, you guard yourself against problems of people misunderstanding what they hand to you. And then let's have a look at this section where we look at a few ways where a bit of pedantry in the language can really save your bacon. Okay, this is a bit of C++, and we're going to play a game of Spot the Difference. There is one character difference between the two, and the output is different from each program. Then the first one, big scary function, and I named it that because it represents a big scary function that does something. In this case, it's 2 lines of code, but in the real world, just pretend that this is huge and you don't quite know the internal details. Somebody else wrote it. So you make a string, put A in it, print that out, run the function, and then print what you've got in the string again. And the reason it prints A, B, A is that the string is being passed. There's no ampersand. It's not a reference. C++, this will copy it. So you're actually making a copy of the string, kind of a slow operation. But you're not modifying the original string. So the string inside the function that's a copy gets modified. The original string doesn't. Then look at the second one. We've added the ampersand. Now you're sending a reference to that string. And so when you add B to the end of that string, you're changing the original. You're not changing your copy of it. There is no copy. You've skipped the time delay of making a copy. So arguably it's faster. At the same time, from the caller's point of view, when you're writing that main function, you don't know in any explicit way that that ampersand is there on the function signature. Because, and even worse, and I've seen this in production, somebody else might have updated that library and added or taken away an ampersand, and all of a sudden that function can change your data. They added the ampersand, and they didn't put a const in to promise not to change it. Or they take the ampersand away, and the big scary function is actually accepting a really enormous data structure. Oops, your whole program performance just fell apart because you will copy that whole bit of data, send it to the function, and the function will work on the copy. which is fine if you're not trying to run it 60 frames a second because you're running a game or a high-performance dashboard. So intent is really clearly stating intent can save the day in this case. In C++, you can help a great deal by using the const keyword. If you're using C++, I strongly recommend it. It will stop you from mutating somebody else's reference, your reference to somebody else's data. Const is not the default. When I'm writing C++, though, it effectively is. I just find myself writing const all the time and taking it away if I do need to make changes. It's still not great. There is a thing called const cast, just in case you really want to ruin people's days, but please don't use it. It is a way to take away the const tag and change things anyway. There's a lot of debate as to why that even exists. Now, Go makes this a lot better. You'll notice on Go, you still are only changing one thing on the function side, so s string, s star string. But on the main side, big scary function s and big scary function ampersand s. You are clearly indicating that yes, I know I'm giving you a reference. Yes, I know I'm giving you a copy. Don't. And so you, the programmer who's writing and consuming the other person's code, has a warning that yes, I'm giving them a reference. Go doesn't have a const keyword as far as I could tell from my reading. Hopefully somebody will correct me if there is one. But I couldn't see a way to take a reference and promise faithfully not to change it, other than writing some documentation promising to do that and hopefully keeping it. Now, Rust takes this problem really seriously, to the point that I've had people tell me that they've hotkeyed buttons to type and mut over and over again for them, which, incidentally, if you're doing that, you've got design problems, shoot me an email. So big scary function, s and mut string, what does that mean? It means it's a reference, you're lending it. Mute, it's mutable. I can change it. If that mute is not there, I cannot change it. It's in the function signature. So what happens if I just sneak that little mut in because I want to change your data in the library? Well, it's not going to compile, because over in main, first of all, to make this work at all, const does exist in Go. Okay, I was trying to get it to work, and I probably ran into my limits of Go knowledge, because it's a language I don't use much. Thank you. Let mute s string. So in order for string to be mutatable at all, excellent, you have to declare the variable itself as being mutable. And that gives you the first layer of protection. But when you lend with the ampersand, send a reference, you also have to indicate whether or not you expect that reference to be read-only or read-write with and s and mut s. And this also ties into the borrow checker. We're going to look very quickly at some issues that you run into with concurrent code in a moment. And this ties into that and also helps you avoid data races. But Rust here is being as explicit as it can, precisely because you want to avoid the problem that we saw in that C++ example, where something changes and now your whole program is working differently, and you spend half a day scratching your head wondering what happened. All right, data races. One of the huge promises that Rust always makes is fearless concurrency. And that always sounds tremendous. I can, stare ahead, be concurrent all day long, and not be afraid. And really, what it means by this is it's taking away some of the big headaches that have been caused by trying to be concurrent in some of the other languages over the years. And so I have a nice little C++ program here. We create a counter, 0. We create a thread. We add to that thread a million times, one at a time. We create, add to the counter a million times in that thread. We create a second thread, add to that a million times. We join on both, print out the result. I tried on a couple of different C++ compilers, didn't get a warning. Every time I ran it, though, I got a different result. I got 110, 3767, 129, 5676. So it's obvious that this isn't working. So once again, if it compiles ship it is a bad idea. This is a data race. And it's happening because we're accessing the counter in multiple threads, and adding is not a single step operation. You have to read the data out, you have to add one to it, and you have to store the result. Now if you have two threads rapidly doing the same thing over and over again, it's quite possible that when one thread reads, the other thread hasn't written yet, you miss one, or other operations are still happening, and you end up with the wrong data consistently. This is one of the reasons that concurrency led to people joking, you know, I had a problem, so I added a thread pool, and now I have 12 problems. It can be the case. It's not always good. Using Go, and I added a little note there that I'm promised not to talk about weight groups because I really do find that syntax just a little strange. In the Go playground, if I make a global variable counter and inside my adder function I add a bunch of times, get the same issue. Now the good news is if you enable the data race detection flag in the compiler, it tells you you've got a problem, you're good to go. The bad news is that for some reason the playground doesn't default to that being on. I hope somebody will fix that. In the meantime, please, please, please make sure that you use that flag if you're writing highly concurrent code in Go, because otherwise you're going to have the same problem as C++, and it's never good when you realize that you are concurrently fixing somebody's invoice and have over or underbilled them. It's not great. Accounting won't be happy. Okay, so in Rust, you can in fact write this same problem. So have a look at this code. We have created a static mutable counter, and then I'm using scoped threads so I don't have to join. Scoped threads are a lovely feature that guarantees that all of your threads are done by the time it comes out. I add to the counter in each of my threads. I'm launching 100 threads, adding to it. I get a different answer every time, exactly the same problem. But Rust is well aware that this is a stupid thing to do, not a good idea. You should not be writing to a static mutable value like that from multiple threads. And the only way to get it to compile at all is to specifically wrap the addition with unsafe, and then you even have to wrap reading the counter to print it with unsafe, because accessing static mutable data is never a safe operation unless you're on a computer that only has one core and can never be threading. So the easy way to do this is to safely is to use atomics. Atomics are a CPU enhanced feature that allows you to do basic arithmetic on primitive types, guaranteed to be in one cycle, come through, supported by C++, supported by Go, supported by Rust. The Rust system for it's a little more pedantic. It forces you to specify your ordering. Relaxed is fine for this type of thing because relaxed means we don't care what the order of operations is, but if the order of operations is always adding, you're going to get the same result anyway. So give this, it gives you the right answer every time. Runs very slightly more slowly, because an atomic operation is typically in the 100 nanoseconds on a modern Intel CPU. A simple addition is closer to 5 to 10 nanoseconds. So you're losing a bit of speed, but you're getting the right answer. And so getting the right answer is generally more important than getting the wrong answer very confidently and very quickly. All right, so just use a mutex. That was the advice for years and years and years in particularly the C++ world. Every language I've found with threads supports mutexes. They're often operating system supported. When they're not, there's usually some way to implement them. You can build a pretty good mutex just with some atomic operations. I highly recommend Mara Bose's book, Rust, Atomics, and Locks, if you want to learn about how these work under the hood. So we have a look here in C++, creates std mutex. Every time we access that counter, we lock the mutex. It's using our AAI, so as soon as it falls out of scope, the mutex will unlock itself, join the threads, print the result. You get the right answer. Go, declare a mutex. Make sure you lock the mutex, add the counter. Again, atomics are more efficient for this, but if you were doing something that doesn't fit naturally into a primitive variable, then a mutex is a better idea. Go does require that you remember to unlock the mutex, but both will give you the right answer. Both will give you the right answer in a performant way. But there's one issue here that neither of them is making you use the mutex. So I've seen this bug over and over again that we remembered to add a mutex. Most of the operations even remembered to lock it and use it. And then there's that one function where somebody forgot to allocate the mutex and accidentally stuck a little race condition into the code. Hopefully you find it. Debugging those can be a seriously bad afternoon. And so one of the design ideas behind Rust was to make mutex use not optional, or some form of synchronization not optional. So if you look at this version, you will notice that the mutex is wrapped around what it's protecting. And so it works like an option, a result. It's an enumeration, or a tuple. You have the outer type, you have the inner type. And using privileged access protection, it makes it effectively impossible to get to the contents of that mutex without locking it first, because the lock function is what gives you the reference, or the mutable reference, to the data inside the mutex that allows you to change it. And so Rust will ensure that if you have a mutex and it's protecting something, you can't forget to use it. I really hope to see this pattern being adopted in more languages, because it's a super powerful construct, very simple. It just forces you to remember to use it. And so that way you can't forget to lock your synchronization primitive, you can't access it without locking, and because of the borrow checker, you can't compile a program that doesn't have some sort of synchronization to prevent the data race. You've got the best of all worlds. Now, you probably noticed it's absolutely horrible ergonomics to have an enormous structure with one mutex at the top, 12 threads all trying to use it, and it goes, everyone's trying to lock it. You've effectively serialized your whole program, because each of the threads is now taking it in turns to access. Doesn't matter that you've got 12 threads, you might as well have one thread, because everybody's accessing it in sequence. It's kind of like when you are on an 8-lane highway and then you realize that you suddenly have to take a country road for a mile. Never good. So Rust allows interior mutability. So you can have a structure, and as long as all of the fields in it are protected in some way, it can be accessed concurrently, remotely, and you can have separate locks for each of the fields. And the borrow checker is smart enough to keep track of this. So if we have our interior mutable structure with a mutex, a read-write lock, and an atomic, different threads are working on that data all at once. First, as long as the threads are accessing different parts of it all at once, and you've used an arc to allow it to be a reference counted, so it'll go away when all of the threads are done with it and only when you've saved it. You can achieve really high performance here by limiting the lock to only the data that you're accessing, not stopping access to other parts of it. It runs really fast. Okay, so why does this work? There's what's called an auto trait called sync. And sync allows you to say that this type can be safely accessed read-only across types. Now the mutex is an interior mutable type itself. So it can be safely accessed read-only from the outside, and it internally then grants access to just one writer. So it falls within Rust's soundness and borrow checking rules. You can either have an unlimited number of readers or one writer. You can't have both at any given nanosecond. And so mutex is obeying the rule, is enforcing the rules. Read-write lock enforces the rules. Atomic U32 enforces the rules. If you write your own spin lock, Mario Bose's book does a wonderful job of showing how to write your own spin lock, impose these rules, give you more tools in your toolkit. So you really can have your cake and eat it. Okay, so what didn't I talk about? I didn't talk about null pointers, probably because this topic's been done to death. Safe Rust doesn't have null pointers. Whenever you might be tempted to return a null, standard library and well-written libraries will return an option for none or some. And because it's an enumeration, you have to either match or if-let one of the other match types to read inside. And so at the very minimum, you are forced to acknowledge that there might not be something there. You can still unwrap and crash if there really should have been something there. But at least you won't be having the ancient C++ and C problem of dereferencing your null pointer, and goodness knows what happens. It will at least crash explicitly. Rust functions are usually designed to avoid problems inside the standard library. For example, the command structure is built to separate the command and the parameters after some early issues where a C program that simply executed cat and then a file name to read a text file could be busted by adding a semicolon to the end of the file name and then some other command. So it would happily execute cat my file semicolon rm minus rf root. Not so good. Rust doesn't have exceptions. I've talked about this in other presentations and in the classes. Uses some types for error handling. So just like Go, you have to acknowledge that an error was possible to use the result of the function. You're forced to have a look at the possibility that things went wrong. Again, you can unwrap and choose to crash if that's what you want to do, but you've got lots of options for cleanly handling your errors and not bloating your binary with an enormous exception handler. Rust enforces strict aliasing. Now, you really only worry about that if you're a C programmer, but what it means is that no two references can point at the same area of memory at the same time. That enables all kinds of compiler optimizations and allows the borrow checker to work. It is possible to write unsafe code that violates this rule, and there are tools that will detect it and yell at you, but it's also possible to break the rule. So if you're writing unsafe code, be aware of that. You will find that a lot of C programs actually turn that on in general. Rust's strong typing makes it easy to avoid unit conversions and wrap unsafe code in safe facades. C++ does the same thing. I would always encourage you to do that. If you need unsafe, wrap it in a safe facade and write some documentation as to why you did the unsafe thing. At some point, there's almost always an unsafe escape hatch if you have to interact with unsafe code. Hardware, code written in another language that Rust can't make guarantees for, it's all there. And some general advice is you can write perfect code in C, C++, Go, Rust, and any other language. Each language in turn has been gradually adding safety belts. Seat belts are good. Seat belts will give you a much higher chance of surviving your collision when you try to run Rust at any speed. Every language decision is an engineering compromise. There's no right answer. Sometimes using a little more safety means compromising a little bit on speed. Sometimes speed isn't what you need. You want correctness. Go with something that emphasizes that. Always use the tool that fits your problem. Rust trades off by being harder to learn. It has a steeper learning curve. But it's really much safer when you get into heavy-duty concurrency, staying close to the metal. When you need the low latency and the high performance, Rust is great. And every language offers you the opportunity to shoot yourself in the foot. Rust and Go make it harder to shoot yourself in the foot, but really bad code in any language is still really bad code. So it's worth taking the time to learn how to not write terrible code. And finally, Rust is not perfect. I often make it sound like I think that Rust is the savior and going to bring about the perfect world peace. It's not. There are holes in Rust. You will find them every now and again. Usually they get fixed. Some of them I just outright disagree with, like for amusement value, look up what you can do by combining std mem forget and some safe transmute calls. You can write some really terrifying code without the unsafe tag thanks to those two. I personally think that both should actually be marked unsafe. But generally speaking, Rust does a great job of helping you not shoot yourself in the foot and is worth learning because of that. All right, lastly, Arden Labs are well aware that developing complex systems with great performance and high confidence and safety is hard. Go and Rust make it easier. Doing it right does require a learning curve, so we offer training, consulting, and staffing services to help you make the best technology stack decisions and tailor your solutions to your customers' problems. And all right, thank you. If there are any questions, I saw a couple go by in the chat. Let's see, Salman asked, can as be used for type conversion for any numeric types or are there restrictions? It can be used for any of the built-in primitive types. I don't necessarily think it's always a good idea to do so. For example, you can use as to coerce a floating point number into an integer. At that point, you lose everything after the decimal point. It's far better to state your intent, use round, truncate, whatever you intend to actually do, because you may want to round up, you may not, but you probably need to know if you wanted to round up or round down, unless that number is completely unimportant. Someone also said Rust is like a mother reminding you to wear your helmet when riding a bike, and that is absolutely right. And from now on, I'm going to be imagining that there's a crab sitting behind me waving a bike helmet at me. And there will be a recording available later. Any other questions? Okay, sorry, I was having troubles reading the banner that just appeared on the screen. How to choose between Go and Rust and Python? That's always a tough one. It's going to depend on what you need to do. Go is fantastic at highly concurrent web service code. Rust is good at that, but you'll write more code to do it. If performance is what you need, though, Rust is fantastic. Python is a wonderful learning language. I'm not going to disparage it, because Python is a great place to get started. Python is great for data sciences. You'll find that a lot of ML and high math is using Python. But what they're really doing is using Python to call code that's written in C or Rust, because Python itself is really rather sluggish, not the fastest language. But when you start combining it with things like NumPy or the Rust-based vector system, I would say Python is well worth learning. But I'm also one of those people who will tell you that it's great to learn as many languages as you can, because it's good for your brain. The more you know, the more you realize that they're all really the same thing and just different ways of expressing what you're doing. Go versus Rust for web services. I don't know if I want to start that bun fight. Go is great if you've got a Go ecosystem going. Use Go. Rust is great if you've got a Rust ecosystem going. Use Rust. If you find yourself in a situation where you really need to be limiting the latency, tying up, or your memory usage, keep it really tight, you can do it in either. Rust is probably going to be the easier option for absolutely clamping down your service. But for me, most of the time when I use a Rust-based web service, it's because it's attached to a Rust system that does something else. And the web service is the gateway in and out for doing that. Okay, so the Rust bundle. I've been here in Miami all week recording a new set of content for the Rust bundle. We're going to be adding a couple of new classes to the bundle coming very soon. I've been working on one on services, and I'm working on one to help you transition from C++ into Rust. I may even manage to get a third one up pretty soon. Oh, and I see there is more questions. Common pitfalls or challenges that developers with experience face when transitioning to Rust. And what strategies do I recommend? Well, Angel, that's too easy. I would say, of course, you want to watch my Ultimate Rust Foundations class. But in reality, the borrow checker is a shock to everybody's system, particularly if you're coming from C or C++. I know I went in with the mind space, oh no, Rust is spending a lot of time solving problems I don't have. Then I ported some code over and discovered I had a whole bunch of problems I didn't know I had, and went through the usual cycle that I see every time of a week or so of, oh, this Rust thing, followed by, hey, I kind of see why it's doing it, followed by, hey, I'm starting to see that Rust has actually made me a better C++ programmer, because now I'm understanding what I was doing wrong. And so even if you're not going to adopt Rust, it's good to learn Rust, because it teaches you how to write safe code by just not letting you compile the alternative. Have we seen any Rust adoption in the high-frequency trading space? Yes. Yes, we have. I'm struggling to think of a good example off the top of my head, but I've spoken to people at RustConf who have been doing just that. Is it planned in the long term to have a tour.Arden Labs for Rust as well? The answer there is I don't know. There is actually a Rust tour that seriously looks like some people just copied the Arden Labs format and tried to start building a Rust one. If I write one, I'm hoping it'll be a little better than that. And that's why I started to learn Rust. Now I can't stop using it. Yep, that's my problem too. All right, do you want to go to the giveaway?
Yeah.
Okay, we are going to spin the wheel and see who's won the bundle. And I'm noticing that this wheel is upside down and tiny, so hopefully somebody will tell me who won. Brian Lee, I think that says. So do
They have to be present.
if you're present, Brian, can you say something and Arden will get in touch with you?
Give them a minute or two.
HFT, I do that now and it is awesome. Well, sounds good to me. I've not worked in that space very much yet. I've worked with lots of people with latency issues. It's actually I'd love to chat with some people who are in that space and see how Rust is working for them. If you want to drop me a line, you can. I think my contact info is up on the website.
We're going to spin again, Herbert.
Okay, we're spinning again because Brian is apparently not here. All right, forgive me staring too close to the camera. I am. Can somebody tell me what this is?
Rodolfo Garcia.
Roberto Garcia? Are you in the chat? Oh, Rodolfo. I'm sorry. I'm reading. My monitor is reversed, so. Well, if Rodolfo's not here, you might well get another chance.
I'm going to do it.
Well,
I'm going for it.
I can't bring myself to sing you guys a song, so. All right, spinning again. I'm Ken Esparta? I'm gonna wait for. You can tell I've got a delay on the. Which website are we using? I honestly don't know for sure. I have some excellent production team here who are taking care of all of the details. I just have to stand here and look pretty, so, or at least try and sound intelligent.
Here we go again.
I guess we're doing another one. Okay.
This is real tense.
Yeah, we're building up the excitement here. Sooner or later, somebody will win.
Oh my gosh, Rodolfo again.
Oh.
I know he's not here.
Oh, between Rust, we know he's not there, so we're going to spin again. Between Rust, Brain Teasers, and Hands-on Rust, they're very different books. Hands-on Rust is very much I've used other programming languages a bit, but I want to learn Rust, and I want to have fun doing it starting from the beginning. The good news is I have a sequel to it coming out very soon. Rust Brain Teasers is more a collection of puzzles, things that might surprise you, corner cases, edge cases. It's a fun little book. You can read it very quickly. It's a tiny book. All right, Ken Esparta is the winner. So go Ken. All right, thank you so much for coming tonight. Today I've had a great time presenting this, and I just want to make it clear, I know it sounds like I'm saying all sorts of bad things about C and C++, but I actually love both. One of my fun hobbies is contributing to the Linux kernel, and that means a whole lot of C. Sometimes it gives me a headache, but it also, in my opinion, makes me a better programmer. I would encourage everybody to try and learn a little bit of C and C++, because it's good to know how this stuff actually works. Even if you'll never use it, it's always good to learn. Thank you.